Hello, this is our narrated version of the PowerPoint for Chapter 5, which is all about condensation and precipitation. It's kind of a fun chapter, and the last chapter for our first exam. Can clouds tell us anything about the state of the atmosphere? And the answer is absolutely. For example, if you notice cirrus clouds approaching from the west, cirrus clouds being the high, thin, wispy clouds that are made of ice crystals. If you notice cirrus clouds approaching from the west, that is your first indication that a low pressure system, meaning a mid-latitude cyclone, is approaching your area. Why does it rain? Well, we'll talk about that. Okay, so what does it take to form precipitation of any kind? Well, first of all, you need saturated air. So you need a lot of moisture content in that air. You also need a lifting mechanism to lift that air to allow it to adiabatically cool and then reach the dew point temperature and condense. And you also need some kind of condensation nuclei. Things like, aerosols. So dust particles in the atmosphere, sea salt, soot, all kinds of things that can act as condensation nuclei. Just a quick discussion here on the difference between hygroscopic and hydrophobic nuclei. I could see a quick multiple choice question about each of these on your first exam. So hygroscopic nuclei are things that are going to attract water. They're going to make a very good condensation nuclei for water. So it's going to be things like sea salt, particles in the atmosphere, dust, for example, pollen, perhaps. So hygroscopic nuclei, what happens here is that water vapor can condense on these particles even when the relative humidity is less than 100%, perhaps well less than 100%. So this explains crackers going stale in your kitchen, salt crystals all sticking together. Cereal can also go stale. And is it necessarily 100% humidity in your kitchen? Probably not. So hydrophobic nuclei, of course, are different. These type of nuclei resist condensation even when the relative humidity is 100% or greater. So this would include things like Teflon, nonstick material for frying pans. It will also include oil. By the way, I'm pretty sure that Teflon is no longer considered safe to have on any item in your kitchen, so throw it out. Don't give it to Goodwill. Condensation. Okay, so again, on these hygroscopic nuclei, water droplets can condense at humidities lower than 100%. Okay, so in other words, hygroscopic nuclei are just ready for condensation to occur. They also tend to form larger droplets than the hydrophobic. Okay, so about those hydrophobic nuclei, they are not efficient condensation nuclei, but they can form tiny droplets when the humidity reaches 100%. They can. So without nuclei, condensation will not occur unless the humidity is well in excess of 100%. Why is that? At very low temperatures, in other words, low kinetic energy, molecules not moving fast, at low temperatures, water droplets will stick together in tiny clusters. How about cloud formation? So what is a cloud? Well, it's water droplets or ice crystals that you can see. Okay, so what does it take for condensation aloft, higher up in the troposphere, as in forming clouds? Adiabatic cooling, remember that is cooling due to expansion as air rises and goes through levels of lower air pressure. Adiabatic cooling causes clouds to form as water vapor condenses in the atmosphere. So when the air becomes saturated, meaning you've hit the dew point temperature, 100% relative humidity, then you need a surface to condense upon. So condensation nuclei act as surfaces on which water vapor or ice crystals can condense. How about growth of cloud droplets? How do they get bigger? So hygroscopic nuclei, also known as water-seeking or having an affinity for water, are most effective for condensation. So they will form condensation droplets much better, easier than hydrophobic, but they also will form larger droplets. And the growth will be rapid at first and then will slow down as that water vapor available is consumed. Okay, so what are clouds? Well, droplets or ice crystals. Can clouds tell us something about the state of the atmosphere? Absolutely they can. We know what it means when you walk outside and the sky is just gray, dark gray as far as you can see, and the clouds are thick, and you know it's getting ready to rain because those nimbostratus clouds are there. Or when you walk outside and you see cumulonimbus clouds, you know that a thunderstorm is forming or approaching. So cloud classification, there aren't many clouds that I'm going to want you to know for your first exam, but we will first go ahead and discuss them at some length, and then I will let you know which ones you will need to know for your exam. Not every single cloud. All right, so first of all, they're based on a couple of things: their form or shape and their height within the troposphere. So as far as the basic forms or shapes go, we have cirrus, high, thin, wispy, white, feathery, made of ice crystals. We have cumulus, globular masses that look like cotton balls or cauliflower in the sky. They generally have a flat base with rising domes. And then stratus, which are in sheets or layers, kind of like strata in a geology class. And then they're also based on their height within the troposphere. So low clouds are going to form below 6,500 feet. Middle clouds will form between 6,500 feet and 20,000 feet. And then high clouds will form above 20,000 feet. Most high clouds are going to be made of ice crystals. All right, so moving on in our cloud classification. So high clouds are going to include cirrus, thin wispy, cirrostratus, thin wispy in sheets, cirrocumulus, thin high clouds in cotton ball looking groups. Low clouds are going to include stratus stretching across the sky, stratocumulus stretching across the sky, but with a cumulus shape, and then nimbostratus, which are going to be your typical rain clouds. Nimbostratus are dark gray, very thick, stretching across the sky. Middle clouds we won't really focus on, altocumulus and altostratus. And then clouds of vertical development, meaning that they're going to grow tall. So what we refer to as cumulus clouds, which you might think of those puffy white clouds that you see under fair weather conditions, meaning blue skies. So really we could call those cumulus humulus. All right, so those are what we think of as the fair weather clouds. When you have high pressure system and you have mostly blue sky, but you got a few of those cumulus humulus clouds looking like cauliflower or cotton balls, and you know you're not going to have rain anytime soon. Cumulus congestus occur when the cumulus humulus clouds are continuing to grow. In other words, you have some kind of instability in the atmosphere, so the air, moisture-laden air, can rise to higher and higher heights. So they tend to be taller than the cumulus humulus clouds. And then, of course, the cumulonimbus clouds, which everybody knows for all the years we've spent on this planet, what we might like to refer to as thunderheads. The cumulonimbus clouds, of course, the tallest, thickest clouds. And they will stretch from the lifting condensation level all the way up to the top of the troposphere. And of course, when you see cumulonimbus clouds, you can expect a thunderstorm. This is a really nice table of all the different cloud types. Okay, so on the left, you've got them listed by, are they high, middle, or low? In the middle column, you have the different cloud tops. And then over on the right, you have characteristics. Now, I have some additional things typed in here. So let's just go through some of these. Okay, so cirrus clouds. Definitely made of ice crystals, thin, fibrous, wispy. Sometimes we refer to them as mare's tails, meaning horse tails. The cirrus stratus may cover the whole sky, may produce halos around the sun and moon. Cirrocumulus I haven't seen in person all that much. I do occasionally see them on images in the Weather Channel. Okay, so they're higher clouds in the form of ripples or waves, sometimes referred to as a mackerel sky. Mackerel is a type of fish, meaning it looks kind of like fish scales, fish skin. Middle clouds, we'll kind of leave that alone. You can certainly read about them on your own if you want to. I will tell you there will be no questions on your first exam regarding the middle clouds. Low clouds are important. Stratus. Low, uniform layer. Remember, stratus means layered or stratified. Kind of resembling fog, but it's not on the ground surface. It's higher up and it may produce drizzle. Drizzle is the tiniest particles of rain, and they're the one where you don't really feel them hitting you, but you know they're there because your clothes are getting damp. Stratocumulus, soft gray clouds and globular patches may have a scallop bottom. Nimbostratus, amorphous, meaning not really having a shape. Amorphous layer of dark gray clouds, one of the primary precipitation producing clouds. These are associated with warm fronts. They tend to be stretch across the sky. They tend to be associated with widespread, moderate precipitation of long duration, all day, couple days. Okay, cumulus, dense billowy clouds, often characterized by flat bases. So cotton or cauliflower associated with fair weather. Cumulonimbus, of course we know these, the thunderheads, right? Towering clouds spreading out on top to form an anvil head associated with heavy rainfall, thunder, lightning, possibly hail, possibly tornadoes. So, some other things we have typed in here. Okay, so when cirrus clouds give way to cirrocumulus, you may have stormy weather in your future. Altostratus clouds are associated with an approaching low. Your first indication of an approaching low pressure system or mid-latitude cyclone are cirrus clouds moving in from the west. Now, which of these might I want you to know for your first exam? Cirrus, nimbostratus, cumulus humulus, cumulus congestus, and cumulonimbus. The other ones we will leave alone. Here's a nice image just giving us a drawing of what these look like. So again, the nimbostratus clouds are important. Stratus clouds are important as well. The cumulus humulus, known as fair weather clouds. The cumulus congestus, starting to get vertical development. The cumulonimbus. And the cirrus clouds. Those are the ones that I'm going to want you to know for your first exam. Here's something that I think I mentioned in a previous chapter, but we'll just bring it up again because I think it's an extra credit question on your first exam. The bottom of a cumulonimbus cloud shows the lifting condensation level. The top shows the top of the stratosphere and the top of the troposphere and the base of the stratosphere, where the troposphere ends and the stratosphere begins, and the anvil head, which is kind of pointy, will point in the direction where the storm is going. Some images here of cirrus, top left, cirrostratus, on the right, cirrocumulus on the bottom. So, an old sailor's phrase, mackerel scales and mare's tails make lofty ships carry low sails. So what are we talking about here? We're talking about the mackerel sky, which was, I believe, was at the cirrocumulus or the altocumulus, telling you that a storm may be approaching. And of course, the mare's tails are the cirrus clouds. And again, when the cirrus clouds are approaching, that tells you that a mid-latitude cyclone is coming. And yes, you might get some weather to contend with from that. And what do they mean by low sails? Well, think back to when boats didn't have, I should say ships, back when ships didn't have any kind of engine, and you had to, sails are all you had. So you had your sails out as much as you could to get where you needed to go quickly. But if storms are coming, you want to bring those sails in, because you don't want gusts of wind catching the sails and knocking your boat over, capsizing it. Just some nice images here of a couple of the mid-altitude clouds, altocumulus on the left and altostratus on the right. Okay, so this is our classic nimbostratus cloud. So dark gray layered clouds may have a ragged base. And by the way, if a cloud either has the prefix nimbo or the suffix nimbus, then that tells you that it's a rain cloud. So either cumulonimbus or nimbostratus. Cumulus clouds, in particular, we would refer to these as cumulus-humulus clouds. Low cumulus clouds associated with basically fair weather. So sinking air, that sinking air may be warmed by compression, allowing for some lift and some condensation, creating these puffy white clouds that look kind of like cotton balls or cauliflower. And these are fair weather clouds. This we have already discussed on a previous slide, but just a reminder that this information from cumulonimbus clouds is a potential extra credit question on your first exam. What we're looking at here is actually not a UFO. It is something referred to as lenticular clouds or lenticular altocumulus clouds, mid-height clouds, also known as lee wave clouds. Why? Because they tend to form on the leeward side of mountain ranges. We are not likely to see these in Pembroke. I don't know that I've ever seen one of these clouds in person myself. I've only seen pictures or video of them before. It does kind of look like a flying saucer, doesn't it? Okay, so this is also a potential extra credit question on your first exam. Aircraft contrails, are they considered to be clouds? And the answer is yes. They are man-made cirrus clouds. So this is kind of neat. I'm assuming this is a satellite image. Which airport is nearby? Not sure. But you do see contrails here. So on average, they're going to cover about 0.1% of Earth's surface. So might we get a slight cooling effect from the increased albedo, meaning that if you have a lot of contrails present, you're going to reflect some of that incoming solar radiation, and it might perhaps reduce the daily temperature range. Is this the answer to climate change? No. Okay, fog. So this is the fog chapter. We will discuss each type of fog, but I will tell you now that steam fog and frontal fog, also known as precipitation fog, will not be on your exam. That being said, we're going to discuss each of these. Fog is cool. It just really is. So what is fog? It's basically a cloud of the ground surface. So when the air at the surface, close to the surface, is cooled, down to the dew point temperature, so you have saturation of 100% humidity, then fog can form. It can also form if you have more water vapor added to that air mass there at the ground surface. And that would be the case in evaporation fogs and saturation fogs. Okay, so we're going to discuss radiation fog, valley fog being a type of radiation fog, advection fog, and upslope fog, also known as orographic fog in particular. Oh, there is a question here at the bottom. How does a fog lift? Pretty sure that's on your first exam. So a fog doesn't really lift. It's not like it's lifting up and away. What happens is when the sun comes up in the morning, as the ground starts to warm, so remember terrestrial radiation, the Earth is spitting that solar radiation back out at a different wavelength. So you're going to heat the troposphere from the bottom up. So the lowest layer is heated first, and basically it just heats enough to evaporate the fog. So the fog will evaporate from the bottom up. Okay, so evaporation fog, these two types of fog will not be on your first exam, but we won't ignore them. We will go ahead and discuss them. Okay, so frontal fog, also referred to as precipitation fog, this occurs when you add moisture. Okay, so when rain falls and then evaporates, thereby saturating the cooler air below close to the ground surface. So this is why sometimes when it starts raining, you might get some fog to form. And the fog wasn't there until it started raining. Steam fog is actually a lot of fun. Okay, so it occurs when you have cooler air moving over warm water. Okay, so the water is warm, and of course it's a source of moisture. So moisture evaporates from that water into the air directly above and saturates the air right above it, creating this low layer of fog. So it's common over lakes. Here is a further discussion of radiation fog. No, we haven't done radiation fog yet. I take it back. Okay, so radiation fog. This is one I will want you to know for your exam. It just has to do with cooling. Okay, so all you need for this to happen, clear skies and high humidity. Okay, so clear skies and high humidity. All right, so heat leaving the Earth's surface in the form of that longer wavelength radiation, but escaping. So the air just above is cool. Okay, so we're talking, let's maybe think about evening time. Evening fog is a good example of this. So the troposphere is losing its terrestrial radiation that it gathered throughout the day. Okay, so clear skies, high humidity. Heat leaving Earth's surface, the air just above is cooled. And if you have a high relative humidity, it means that you don't need a big change in temperature to reach the dew point temperature. Just a small change, a little bit of cooling. All right, so because of the high humidity, a small amount of cooling is all that is needed to reach the dew point temperature. So heat radiating from the surface at night, cooling the bottom air until it reaches saturation. And this can form some really thick fog, particularly this can happen in the mountains. Orographic fog is not the only kind of fog that happens in the mountains. So I think fog is very pretty myself, but is it fun or safe to drive in? The answer is no. And in case we go into lockdown before we get to this chapter, in case I don't get a chance to ask you guys this in class, what should you do with your headlights when it's foggy? Does anybody know? Should you turn your headlights on at all? And the answer is yes, you should, because you need other cars to be able to see you. Okay, so you turn them on low beam, and even though the low beams may not help you see any better, it lets other cars see you. Now, you don't turn them on high beam. Why? Because you turn the lights on high beam, and all those droplets of water are just going to reflect that light back to you, and it actually kind of, it makes your visible, or your vision, your field of visibility, even worse than it was before. So when it's foggy, yes, turn your lights on, but have them on low beam. Valley fog, I will want you to know this for your exam. It's a special type of radiation fog. So what happens here, so imagine you're in a mountain range, but you got a valley there, a river valley. So the sun is getting low in the sky, and you're going to start to lose heat, and you're going to start to cool, and you're going to cool from the ground surface up. But what's going to happen here is that the higher elevations, mountains on either side of the valley, are going to cool quicker or first. So you're going to form fog on the upslopes, but that fog is going to be, that air with the fog, it's cold and it's dense. So it's going to sink downslope into the valleys. So valley fog is a type of radiation. All right, so some images here. Valley fog in California, up there on the right. And then down there on the left, valley fog in the Appalachian Mountains. So one of my family members, way long ago, when my brother and I were kids, and we would go camping in the mountains, and we would be driving early in the morning to get to where we were going, and there would be this fog. And this family member would say, "Look, it's the groundhogs making coffee." Okay, so the Central Valley of California, what is it known for? Well, there's agriculture here. It's where the cultural thing of Valley Girls comes from, which was rather silly, but you know, hey, it was the 80s. What are you going to do? But it also is a place where valley fog will collect. So you see the satellite image there of valley fog in the Central Valley, and then you see the road. And yet again, there's a sign warning drivers that fog is there. But because of the fog, you don't see that sign until you're kind of right up on it. Advection fog is another type of fog I will want you to know for your first exam. Okay, so advection fog occurs when you have warm, moist air moving over a colder surface. And as this warm, moist air moves over a colder surface, it's going to cool. Therefore, the air there at the bottom can drop to the dew point temperature, and you can form fog. Okay, so examples of advection fog. In the winter, when you have warm, moist air from the Gulf of Mexico and Atlantic moving over cold, snow-covered surfaces in the southeast and Midwest. You might ask, when do we have snow-covered surfaces in the southeast? Well, it occasionally happens. Okay, this is probably more likely to happen in the Midwest U.S. This is my favorite example of advection fog. Of course, everybody knows this is San Francisco because you see the Golden Gate Bridge there. So what happens here is that, remember, this is on the west coast, meaning that for the Pacific Ocean Basin, it's on the right-hand side of the ocean basin, means that the surface current there is cold, okay? So it's called the California current. So the cold California current that is moving south, skimming the west coast of the United States, you end up with moist air coming in from the Pacific, moving over the cold California current, cooling and forming fog. So this is advection fog in San Francisco. I just think this is beautiful. I mean, you can't see, well, do any of you see the water down there, San Francisco Bay? No, you can't see it because look at all that fog. Okay, so upslope fog is a lot of fun, and upslope fog will be fair game for your first exam. So this is formed from the orographic effect. So this is part of orographic lifting, basically. Okay, so an example here is air moving from the Gulf of Mexico toward the Rockies. So relatively warm, moist air from the Gulf of Mexico moving into the United States and encountering the Rockies. It's amazing how far air masses can travel and how far air masses from the Gulf of Mexico can travel. In a later chapter, like maybe chapter 8, we'll learn about air masses. That's actually a fun chapter, relatively straightforward. So this warm, moist air moving in from the Gulf of Mexico, hitting the Rockies, then gets pushed up and over the Rocky Mountains. And just like in our orographic lifting, as that air is rising, it's expanding and cooling. And if it cools quick enough at the surface, then you have condensation at the surface, and you're going to form fog instead of clouds. All right, so might this type of fog also form in the Pacific Northwest? Cascade Mountains, Olympic Mountains? Absolutely, I think that would happen. Could that potentially happen in the Appalachians? Sure. Okay, frontal fog, also known as precipitation fog. This is not on your exam, but we'll discuss it briefly. It's also known as a type of evaporation fog. Actually, we may have briefly discussed this before, but this is a little bit better slide. So this fog is formed by adding more water vapor to the air. So raindrops falling from relatively warm air above a frontal surface evaporate into the cooler air below and cause it to reach saturation. So look at the top left. That's frontal wedging. Okay, kind of similar to what's on the bottom left. So you have a cold air mass over top of you, but you have a warm front moving in. That warm air gets pushed up and over the cold wedge of air. That air is going to cool and condensation will happen, and then rain will be produced. But as that rain is leaving the warmer air aloft and entering that wedge of cold air, it's going to cool enough to reach the dew point temperature, and that can form fog during the rain. Okay, so I thought there was going to be a picture of coffee fog. Maybe there is later. But so if you've ever gone camping and it's a very cold morning and you're making coffee, either on a camp stove or at a campfire, and that coffee is really hot, well, you can get a little bit of steam fog right atop the coffee. Okay, so again, how does a fog lift? It doesn't actually lift or rise. The sun warms the ground, which in turn heats the air near the surface first. So basically just that the fog evaporates from the bottom up, which kind of looks like it's lifting. So this is a neat little image here. We are looking at days with heavy fog. And of course the color coding there gives you an idea of how many days in a normal year you might have heavy fog. And then they have labeled some of these types of fogs. Okay, so what do we see? Coastal areas, especially where you have cold water currents, like on the west coast, have lots of fog. Advection fog, and of course they can have radiation fog as well. The Great Lakes have a lot of advection fog and radiation fog. The Appalachian Mountains are going to have upslope fog, valley fog, which is a type of radiation fog. Of course, they'll have radiation fog as well. Anywhere that cools can have radiation fog. You see some advection fog and radiation fog from the Gulf of Mexico moving into the United States. And then, of course, advection fog up there in New England and getting into Canada, Newfoundland, because up there you don't have the Gulf Stream current. It has already headed east to Great Britain, and now you have this cold water current coming down from the Arctic. So, where do you see the most fog? Do you see a pattern there? Do you see purple and red in the Appalachian Mountains? In the Cascades? In the Olympic Mountains? How about the Rocky Mountains? You do see some fog in the Rocky Mountains, not quite as much as you see with the Appalachians or the mountains on the west coast. So they no longer have the geode animations and graphics, unfortunately. I don't know what happened there. They were actually really good. So you won't see any of that listed in the learning modules or in your e-text or the modified mastering. Okay, question. The word radiation in the term radiation fog refers to what? Okay, is it A, infrared radiation absorbed by the fog? Is it B, solar radiation, short wavelength coming from the sun? Is it C, radiant energy lost by the ground? Is it D, radiation energy given off by the fog? Is it E, nuclear fallout? And that should say F, not another E. Or is it none of these? So what do you think, guys? Radiation fog, cooling, creating fog. So that answer is going to have to be C, isn't it? Radiant energy lost by the ground. And the correct answer is, of course, C. Radiant energy lost by the ground. Okay, questions. If you're driving through hilly terrain at night and there is dense fog in the valleys while the upslopes are clear, then what type of fog have you encountered? So you might immediately say, well, it's got to be valley fog. Okay, that's true, but remember that valley fog is a special type of some other fog. All right, so is it radiation fog or a graphic fog? I mean, it is in the mountains. Is it advection fog? Do we have any water nearby? Is it steam fog? And again, do we have water nearby? Is it frontal fog? Do we have rain? Did you guys guess correctly? It's going to be radiation fog. Remember, the valley fog is a type of radiation fog. Correct answer, radiation fog. Okay, so I think now we're going to have a brief discussion regarding a couple of different means by which rain droplets grow. All right, so first what we're looking at here is, well, for scale, they have a typical raindrop 2 millimeters across compared to a typical human hair, showing also large cloud droplets, a typical cloud droplet, meaning it's still in the cloud, it's not heavy enough to fall as rain, and then condensation nuclei, and they are comparing these in millimeters. So an average cloud droplet may fall out of the cloud, but it's going to evaporate before it hits the ground. So droplets need to be big enough to fall out of the cloud and not evaporate on the way down. How does that happen? Okay, so two different types here. All right, we will begin with number one, the Bergeron process. So this is precipitation coming from cold clouds. Okay, so this precipitation begins as snow and then melts on the way down, only occurring in the middle and high latitudes. Well, we are in the middle latitudes here, in Pembroke, Southern Pines, Fayetteville, wherever. Okay, so most of our precipitation, rain, actually begins as snow, but boy, it's not snow when it hits us. That's the Bergeron process. And then there's the collision coalescence process, which is precipitation from warm clouds. So we're talking either in the lower latitudes, like within the tropics, 23.5 degrees north latitude down to 23.5 degrees south latitude, or perhaps in the middle latitudes, like where we live, after snow created from the Bergeron process melts as it is falling down through the troposphere, encountering warmer air on its way down. Just some interesting stuff here. Oh, we finally get to talk about supercooled fluid. Good. Okay, so Bergeron process, cold cloud precipitation. Cloud droplets do not freeze at 0 degrees Celsius, 32 degrees Fahrenheit. Okay, so this is cloud droplets, you know, higher up in the troposphere. They do not freeze until nearly negative 40 degrees Fahrenheit. Okay, and that has to do with physics. If you want to know why, you know, well, you can Google that, and it's a neat story. So we call this supercooled fluid. All right, so it's water that's in a liquid state and it's below freezing and it's very cold, but it's not just going to condense easily. Okay, so supercooled fluid. So this will produce things like freezing rain, glaze, and rime. So this supercooled fluid within our clouds will freeze when it comes into contact with solid objects. Okay, so in the Bergeron process, you're going to begin with these tiny ice particles. And as they move throughout the cloud and encounter supercooled fluid, then, once the supercooled fluid hits a solid object, even like a tiny ice crystal, well, then it's going to condense and add another layer of ice. So when the ice crystals become large enough, then they will fall, and they will, after they've grown in size enough, as they keep encountering these water droplets that freeze onto them, eventually these frozen particles, snow basically, will fall from the cloud. But in the warmer months in the mid-latitudes, this will melt on its way down, and it will simply hit us as rain. Okay, so in the mid-latitudes, much of our raindrops begin as ice crystals in the Bergeron process. Just to let you know, temperatures in the upper troposphere, where commercial jetliners typically fly, an average of -58 degrees Fahrenheit. That's just crazy. No wonder they sometimes worry about ice on planes. You can read over this if you would like to. Just a little bit more about the supercooled fluid. All right, so just a little bit more here about the supercooled fluid and the Bergeron process. So supercooled water droplets will freeze on contact with ice crystals. When the crystals become large enough, they begin to fall. They may grow as they encounter more supercooled droplets. When the surface temperature is 39 degrees Fahrenheit or above, it hits us as rain. If it's below that temperature, then it can hit us as snow. Now, we know from experience here that sometimes we get a little bit of snow. It might spit some snow, but if the ground is too warm, as soon as it hits the ground, it melts. So what form the precipitation takes, be it rain, sleet, snow, or freezing rain, will depend on the surface temperature. So more on the Bergeron process. It's responsible for producing freezing rain and glaze, think ice storms. Okay, so here we have the relative humidity with respect to ice. When relative humidity, oh wait a minute, I don't like this title. I did not type this title. This is from the textbook authors. Relative humidity with respect to ice when relative humidity with respect to water is 100%. So you see there that as the temperatures get cooler, the relative humidity with respect to ice can grow and get above 100%. So again, you have the supercooled fluid within your cloud droplets, within your clouds. Okay, so enough of the Bergeron process. Let's talk a little bit about the collision coalescence process. Okay, so again, this tends to be either in your lower latitudes, like in the tropics, what we refer to as warm cloud precipitation, or this collision coalescence process will take over in the middle latitudes after that ice snow falls and melts. Okay, so what happens in the case of the warm cloud precipitation? Humid air, the air has reached the dew point temperature, so the air has reached the lifting condensation level as far as lifting mechanisms go. You need hygroscopic nuclei present to allow condensation and the formation of large droplets. And so these droplets can then collide with smaller droplets, and they remember that water has surface tension, and then they coalesce into droplets that are large enough that they can fall and hit the surface without evaporation. So here's a nice drawing trying to show the collision coalescence process. And again, if you have the hygroscopic nuclei there, that helps speed things along. And don't forget the hygroscopic nuclei will cause condensation to occur at relative humidities below 100%. Again, making crackers and cereal and chips perhaps stale. Okay, so more on this collision coalescence process. Larger droplets fall through a cloud. They keep growing larger as they collide with smaller droplets and coalesce. And it's not just when they fall. They could be moving upwards in an updraft, encountering other small droplets and growing. How many cloud droplets does it take? Oh, a million or so. So after a million or so cloud droplets coalesce, the rain droplet is large enough to fall to the ground without evaporating. So due to the huge number of collisions needed to grow to raindrop size, clouds of vertical thickness have the best chance of producing precipitation. Basically, your nimbostratus and cumulonimbus clouds. Okay, this is a neat table here. It's showing the velocity of falling raindrops based on their diameter. So as you can see, as the raindrops grow larger, they're going to fall at a higher rate. They're also going to have a better chance of hitting the ground without evaporating first. Okay, virga. I might want you to know what virga is for your first exam. Pretty easy stuff. So this is basically rain that falls out of a cloud but evaporates before it can even hit the ground. Okay, so this is common in the desert southwest where it's more arid. Why is it called virga? That's Latin for streak. Do they kind of look like tiny tornadoes coming down from those clouds? They do, but it's not tornadoes. It's just rain evaporating before it hits the ground. Here's another example of what virga might look like. Okay, so now we're going to get into what I think is our last topic for this chapter. I forget sometimes how long these first 5 chapters are, but they're basically introducing all the concepts that will then, set the stage for the later chapters. I'm always happy to get these first 5 chapters in the first exam out of the way because things get more fun after that. So precipitation. It's called rain if the droplets have a diameter of at least half a millimeter. Most rain is going to come either from nimbostratus or cumulonimbus clouds. Remember, if you have nimbo or nimbus attached to the cloud name, it tells you that you're going to have rain. Drizzle and mist are smaller and are not really considered to be rain. I think earlier in this PowerPoint, I may have said that drizzle was the smallest precipitation. I was wrong. I forgot about mist. Okay, so drizzle is less than half a millimeter and may come from the nimbostratus clouds or from the stratus clouds that don't often produce rain. And then mist is the smallest, and it's almost imperceptible when it hits the ground. Okay, snow. We know what snow is. We hope to see it someday. I'd like to see it today. Frozen ice crystals. So at very low temperature, the air is very dry. So when the air is really cold, but it can still snow, that's when you're going to get what they call powder, a fine snow. So temperatures below 23 degrees, your Fahrenheit, temperatures below 23 degrees Fahrenheit in general, if it snows, you get that powdery snow that the skiers love. But if it's above 23 degrees Fahrenheit, it makes a wet snow. So the skiers don't like it as much, and I guess kids that are off of school and want to have a snowball fight or build a snowman, they're going to love that stuff. But it can bring down power lines and everybody's electricity and therefore their heat source during the snowstorm. Okay, sleet. You will need to know the difference between sleet and freezing rain. So sleet occurs in the wintertime. It's definitely a wintertime event. Okay, so what happens here is that you have a layer of air that's above freezing overlying a layer of air that's below freezing. In other words, a temperature inversion. Okay, so raindrops that probably began as snow mid-latitudes and then they melted on the way down and became rain, but then they hit a cold layer of air before reaching the ground, and then they freeze into these tiny little ice pellets. So small ice pellets the size of raindrops. All right, so how do you know that it's sleet and not just fine rain that is hitting you? And the answer is sleet bounces. I've seen this. I've seen it hit my car and bounce driving, or the front porch, or my gloved hand when I lived in Laurinburg. Sleet definitely bounces. Freezing rain is different from sleet. You need to know the difference. Freezing rain is also referred to as glaze. What happens here is raindrops become supercooled in a layer of below freezing air near the ground. It's too thin to properly freeze those drops. So you basically have, and of course this tends to be a wintertime event, you have supercooled raindrops, and they don't encounter a thick enough layer of cold air to freeze. So when they hit the ground or any solid object like your car or the power lines, it's still a supercooled fluid like you expect up in a cumulonimbus cloud. Okay, and then it encounters all this surface area to act as condensation nuclei, and it's going to freeze to ice as soon as it hits a solid surface, and it just makes this glaze of ice over everything. So rime is something I've never seen in person. I've only seen pictures of it. Ice crystals formed from either supercooled cloud droplets or supercooled fog hitting objects that have temps below freezing. I believe that rime is more likely to occur in the mountains. Hail. You will need to know what hail is. I think at the end of this I will recap which types of precipitation I want you to know for your first exam. Hail might be ice, but it's not a wintertime event. Okay, this is a warm weather event, spring, summer, maybe early fall. This is produced only in your cumulonimbus clouds in thunderstorms. You're more likely to get hail if it's a supercell thunderstorm, and especially, well, if it's either you're more likely to get hail if that thunderstorm is due to a cold front approaching, and especially if it's a supercell thunderstorm. So you have these really fast updrafts present in the cumulonimbus clouds. They can be moving at 100 miles per hour, and you've got all this supercooled liquid present. So the hailstones begin as small ice pellets called grapple, and they are going to just go up and down through that cloud with the updrafts and downdrafts. And they're going to keep going through that supercooled fluid, and every time they do, they add another layer of ice, and then eventually they get heavy enough to fall to the ground. Okay, so again, the hail is not going to leave the cloud unless it becomes big enough to be heavy enough that it can fall without melting. Okay, so here is a nice drawing showing that you begin with grapple, ice nuclei, in the higher levels of the cumulonimbus cloud, and then it kind of goes on this path up and down with updrafts and downdrafts until it becomes big enough to fall to the ground. At this point, let me tell you which types of precipitation I really want you to know about. I want you to know about hail. I want you to know the difference between sleet and freezing rain. As far as rain and snow go, drizzle and mist, I don't think those need to be on the exam. You know what those are well enough, but I will want you to know just a little something about the Bergeron process and the collision coalescence process, and the fact that in the middle latitudes, most rain begins as snow. So here are some just basic types of snow crystals. Have you guys ever heard that there are no two ice crystals that are ever the same exact shape? I'm not quite sure I believe that. So this is kind of neat. This is showing the temperature profiles needed to produce either rain, snow, sleet, or glaze. Remember, glaze is freezing rain. So let's look at this. Let's start with rain. In the case of rain, and this is mid-latitudes, by the way, notice your rain is beginning as snow. It's melting and hitting the ground as rain. Okay, and then over there on the top right, snow. If you have the temperatures cold enough all the way to the ground, again, this is the Bergeron process. Middle latitudes, that precipitation is beginning as snow anyway, coming out of that cloud, and it just simply doesn't melt on the way down. Okay, in the case of sleet, wintertime event, you have, again, Bergeron process. The precipitation falls as snow, but then you have a temperature inversion. Okay, so it's hitting a layer of warm air on its way down and melting as you would expect, but now the temperature inversion takes place, and the cold layer close to the ground is thick enough that those water droplets freeze again, and then you get sleet, ice pellets that bounce and coat the road. All right, and then the last one there on the bottom right, what does it take to form freezing rain or glaze? So again, mid-latitudes begin with the Bergeron process. That snow is going to melt into rain as you expect, but if you have a temperature inversion and you have a thin layer of below freezing air at the ground surface, maybe due to overnight cooling, well, that rain is pretty cold as it's falling, and it's not going to freeze as it goes through that cooler air at the surface because that air is not thick enough, and it hits the ground as supercooled fluid and then instantly creates a glaze of ice over everything. So here's a nice image showing the formation of sleet. This again is a wintertime event, and if you're wondering, gosh, how do we keep having these temperature inversions? Well, this is a common way to get a temporary temperature inversion anyway. Let's say that Pembroke sits in that blue wedge. You got cold air above you, but there's a warm front moving in from the west. Air that is warmer, and it's got some moisture, and it's lifted up and over the wedge of cold air. Again, we refer to that as frontal wedging or frontal lifting. And you have the air rising, cooling adiabatically, condensing. You have snow falling, Bergeron process, melts to form rain in that warmer air mass. But then below is the cold air wedge that's on its way out. And the droplets freeze again and form the ice pellet. Wow, look at this. Boy, that's not a good day to go and try and drive. So freezing rain, glaze, forms when supercooled raindrops freeze on contact with objects. All right, so that's just crazy. I mean, you can't drive anywhere. Salting the roads is not going to help. Having four-wheel drive does nothing for you on ice. You just shouldn't be driving. And we hope that all the first responders live close enough to their jobs that maybe they could carefully walk there, or maybe they just stayed overnight in the hospital to work another shift the next day. Anyway, school's canceled, that's for sure. Take a look at those power lines and telephone lines. My goodness, they're coming down. This was a record. I seriously doubt it's still a record. But roughly, I don't know, close to 10 years ago when this edition of the textbook was published, perhaps more than 10 years ago. This was a record hailstone. Okay, so this is back in 1970 over Coffeyville, Kansas. It weighed 1.67 pounds. Now look at that hailstone in that person's hand. So notice the rings, okay? So every time the hailstone goes through supercooled fluid, it adds another layer of ice. So this is what hail can do. Wow, so this was a storm back in May of 1995. High winds and hail the size of baseball. That's terrible. Oh my goodness, people got killed. A lot of properties got damaged. Imagine being outside and being hit by a hailstone that was the size of a baseball. That would be horrible. So this is rime. This is something I've never seen in person. So again, this is from supercooled fog or supercooled cloud droplets at the ground surface freezing on contact with objects. And it looks like little needles, ice crystals. Okay, there will be nothing about rain gauges on your exam, but this is a typical rain gauge. Okay, so how is snow measured? By snow depth, how much you get within a 24-hour period, and then changing that to its snow water equivalent. Here is average annual snowfall in the contiguous United States. So North Carolina, yeah, we're not surprised. We're at the bottom, anywhere from 0 to 8 inches. So my old stomping grounds there in the Appalachian Mountains get a good bit more snow than we get here. I want to point out Buffalo, New York. So see if you can find, I think that's Lake Erie, the one that runs kind of northeast to southwest. Buffalo, New York. Gets a lot of lake effect snow. Okay, this I think is our last topic. I hope so. I'm running out of steam. Just for fun. So can we do anything about the weather? Cloud seeding, fog dispersal, hail suppression, frost prevention. Cloud seeding. This is where you hire, well, you're a farmer and you want rain, and the meteorologists tell you that there's enough moisture in the air that you could get rain. So you hire somebody with one of those crop duster aircraft to fly and release silver iodide crystals from the back of the plane to act as condensation nuclei. Does it work? I'm not sure. They do occasionally do it, so perhaps there's been some tiny success here or there. I don't think it's super successful. Second one there, fog dispersal. Shooting dry ice, which is frozen CO2, into fog to try and disperse it. I feel like that's not going to work at all. I don't think we do that anymore. Hail suppression cannons. Yeah, we definitely don't do that. Firing smoke particles into thunderstorms. Pretty sure that doesn't work. Frost prevention, we do some of that with agriculture, especially citrus fruits. So this is an example of cloud seeding. Cloud dispersal, I guess they attempt to try to do that. That would go back to that thing with the hail suppression, I suppose. Here's a little something about cloud seeding. So that drawing on the left is a hail suppression cannon. Pretty sure it just did not work at all. And then there on the right are some very large hailstones. My goodness, those are scary. Okay, so frost prevention is a real thing, and we still do it, and there is success with this. So what happens is, say Florida, California, citrus fruits, but there's frost in the forecast, and you don't want all of your crops to be ruined. So if you release water in citrus groves, what this does is it releases latent heat when you get ice to form around that fruit and can prevent frost. So it may sound counterintuitive to spray water onto your fruit when it's about to frost, but you spray water onto your fruit and it forms this layer of ice, and that is condensation, and that's going to release some heat energy and basically, I guess, form a protective shell around the fruit, preventing it from frosting. Something else that can be done are wind machines. And again, you'll notice there's an orange grove there on the left, mixing warmer air aloft with colder air on the surface, assuming that in your frost event you have some kind of temperature inversion. Orchard heaters and smudge pots. Okay, so on the, which one is which? Maybe they're both the same. So what happens here is that these heaters, and they're burning, some kind of fuel, which would create, some particles being emitted. I guess that's why they're also called smudge pots. So they're providing warmth, warm the air around your citrus trees and fruit, but also it's releasing soot that is providing condensation nuclei so that you'll get some of that ice to form on the soot and less on the fruit. A punch hole cloud. When an airplane basically just punches through the clouds, it's taken off. That's it.